3 weeks before drop day or something. Right? The withdrawal day is a while.
They don't get their money back anymore.
Right, that's true. But that you only get a week for that. So. All right, so when we first left our heroes, they were calculating concentrations. Mass percent, mass by volume, molarity. If you haven't posted your data from the last lab to that spreadsheet, please do so because your classmates are all counting on you to use that data in preparing the report. I believe the last I checked, there is actually enough data up there that you can plot a curve. So if you've been waiting and waiting and waiting, it's not going to be a great curve, but there should be enough data up there that you can at least get something. So go ahead and finish that part.
I thought we could do that in class, but I guess there's not enough people here anyways.
Right. We did it. When did we do it?
We didn't have time though.
We did some last week, but we didn't quite have a lot of time and some people left. And then, so it's there. You click on the link. You should be able to edit all the information so you can type in your own stuff and put it in there. But anyway, there should be enough to finish that so you can bring that to lab on Tuesday. So we talked about different kinds of solutions, and one thing that came up was this idea of isotonic. So we're going to talk a little bit about that today, what that means, and that's going to be a big part of the lab on Tuesday also. So first we have to talk about a couple things that are related to solutions, but not quite. And that is suspensions and colloids. Does anybody know what these are? How do you define these? How are these different from solutions? Somebody last night said, well, a suspension is in your car. Yes, I guess I can't argue with that, but that's not this kind of suspension. Any ideas? Has anybody ever heard about of a suspension, like in a medical context or something, anything like that?
Would it mean that it's lighter, like that it's floating?
Yeah, floating is really the key here. So a suspension is actually larger particles dispersed in a liquid. So a solution, in a solution, a compound is broken down to its molecular level. Individual molecules have broken apart and are surrounded by solvent, by water or whatever, that are holding them in solution. A suspension is large particles, things that are much, much bigger than molecules. And so they're dispersed in the liquid, meaning they're just kind of floating there. And if you let a suspension sit for long enough, it'll settle. That's kind of the key of a solution, of a suspension.
So not like ice.
So not like ice.
And will dissolve. This is something that will not completely dissolve.
It will not dissolve, and but it still makes a homogeneous mixture when you shake it up. So when you shake it up, it kind of looks like all the same, but then if you let it sit, the stuff will all make its way to the bottom after a while.
Can you give us an example? Like
salad dressing, sure.
shakes?
Like what?
Shakes.
Shakes, like milkshakes?
Not milkshakes. Some shakes that I make, or like a protein shake.
Oh, that kind of stuff. Yeah, that's a good example. So like that kind of, those proteins are large molecules that are being held in there, and after a while they'll settle down to the bottom. A lot of medications are given as suspensions. If you ever have seen like kids antibiotics, that like the pink stuff that kind of tastes like bubble gum or whatever, you have to shake it before you give it because it's kind of this thick stuff, and then after time it'll settle to the bottom. So it'll settle over time. Suspensions can be filtered or separated by filtration. So if you take a suspension and you pass it through a filter paper, the solid will stay on the filter paper and the liquid will come through the bottom. Another thing about actually both of these is that you generally can't see through them. They're somewhat opaque to light. You'll notice a solution looks really nice and clear. It might be colored, but it's very clear. You can see all the way through it. A suspension, like milk, looks very opaque. Now, milk is not technically a suspension because it's homogenized and it won't settle out over time. So that actually fits in this next category of a colloid, which is just smaller particles and suspension larger than a solution. So this is kind of the in-between thing. Yeah.
But you said milk, so with raw milk, because when you separate the cream,
Right.
so it starts out as a suspension, but what homogenized means, it's boiled, right? It's heated.
No, homogenization just means it's shaken mechanically really hard.
And
So
then
you
it-
take milk.
So you can turn one into the other.
Yeah, because you're
and-
breaking apart those individual particles really small. Yeah. Milk might be a tricky example because I can see how it might fit in either of these parts. There's so many things in milk. It's a lot of stuff in there. So colloids is kind of in the middle. Colloids generally will not settle or filter. So if you try to pass it through a filter paper, it'll all still come through. It'll still look kind of cloudy on the bottom. And it'll stay in suspension indefinitely. It won't filter out over time. But it still kind of looks like that. It still has that kind of milky look to it where you can't see all the way through it. It's not totally clear. And the way you separate things from colloids is with something called a semi-permeable membrane.
Is that all one word?
What?
Is that all one word?
It's hyphenated. So we'll talk about what that means here. There's my picture. Here's a picture from your book.
So all cells filter colloids?
Right. So you've got a mixture here where the red particles are on the bottom here. The red squares are settled out. Those are the suspension particles. The orange circles are the solution particles. Those are all suspended in solution. And then the triangles are the colloid. So over time, the red suspension particles will settle out. The other stuff will still stay in solution. If you pass this thing through a filter, the red squares will be caught by the filter. The other stuff will mostly all make it through. And then if you put this solution in a bag of a semi-permeable membrane, which an example would be like a cell membrane or a cellophane, like plastic wrap, and we'll use some of these in lab on Monday called dialysis bags. Yeah.
What is plastic wrap like?
What?
Plastic wrap.
It's actually technically a semi-permeable membrane, so it can do this. It can let solution particles through.
Oh, not that you can see though.
Right. Right. So in this case, the stuff is in the bag, and the yellow solution particles are getting out, but the other stuff is all too big and will stay in the bag. So you can try this actually if you take like plastic wrap and you make a little container out of it, like a rubber band or something, put salt water in it or sugar water, and then put it in a bowl of clean water, and eventually there will be salt in the clean water also.
I thought you said the colloids would go through the semi-permeable.
No, only colloids are trapped by a semi. That's how you separate them. Right.
Get stuff in it.
Right. And that's why we talked about earlier, a solution, we say it's a homogeneous mixture, but it's really a special homogeneous mixture. Because even at the molecular level, it's still, it's involved with its solvent in a really close way. These other types aren't quite that. So speaking of semi-permeable membranes, we can talk now about osmosis. So what's osmosis? You heard that term before? Yeah, it's the movement of water through a semi-permeable membrane. I guess it is one word here. And this will move from, water will always move from an area of low concentration to high concentration. So here's a picture of this. You take a beaker and you put a semi-permeable membrane in the middle, or some container, I guess. There's pure water on one side, there's water and salt on the other side. So what happens is the water moves through the semi-permeable membrane to try to equalize the concentration. So from low concentration to high, water will move here trying to increase the concentration of that. Actually, water is moving back and forth, but there's more pressure pushing it toward where the solute is. So it's going to move into the area of solute. And this is actually creating a pressure because it's pushing that water up against the atmosphere. So this motion of the water kind of pushing through that semi-permeable membrane is known as osmotic pressure. So we say that it's exerting a pressure across that membrane, pushing the water in to the area of more concentration. Because it wants the concentration. If you put two equal concentrations, water will just move evenly and it won't change. If one has more concentration than the other, the one with more concentration will get the water to try to become less.
So it's moving towards the higher concentration of solute.
Right.
Not against the high, not to a higher concentration of water.
Right.
Where there's salt.
Right, to the higher concentration of solute. So that's known as osmotic pressure, and that's where these other terms that we saw last week come from.
Because the solution is the ions in the solution.
Right. Yeah. Because when the water moves across to be with the solute, it now has stronger interactions because it can interact with the solute. So that's what kind of pulls it on that side. That's like the driving force of that process.
And the osmotic pressure then is on the side where the solute is? Is it the pressure
Opposite.
against the membrane?
Yeah.
Oh, so it's the pressure from the side of lower concentration.
Right.
Moving that way.
Right. So that gives us these three words: isotonic, hypotonic, and hypertonic. Isotonic, iso means the same. So isotonic is a solution that has the same concentration as, we'll just say in general, bodily fluids. The reason that's important is that it means that when an isotonic solution is introduced into your body, the osmotic pressure across the cell membranes is equalized. So there is no pressure into or out of the cells because the solution or the fluid has the same osmotic pressure as the inside of the cell. So then a hypotonic solution is going to be one with a lower concentration than what is in the cells. And so let's think about what would happen in that case. So you've got your cell with a certain level of solute concentration. And let's say we put this then in a fluid that has a lower solute concentration. Which direction is the water going to travel? Into the cell or out of the cell? Into, right. So the water, yes. So water goes from where there's less solute to where there's more solute. Yeah. So water is going to flow into the cell from the lower concentration around, which causes the cell to swell and potentially burst. So then hypertonic is going to be the opposite situation. A higher concentration. If this is our cell, if there's a higher concentration of stuff in the solution around it, the water flows the opposite direction out of the cell and the cell can collapse. So there is an osmotic pressure then in each of these solutions over here. In a hypotonic solution, the osmotic pressure is from the outside surrounding fluid into the cell, so a higher pressure. And then a hypertonic solution, we might say, has a lower osmotic pressure because the water is being pushed out of the cell into that surrounding matrix. And the book has some nice pictures of this happening, which I have last bit of time here. So you can see this. Can you see that? Should I turn the lights off? Turn it off real quick. So in the first case, you've got an isotonic solution and some nice, healthy-looking red blood cells. In a hypotonic solution, water is moving into the cell more than is moving out, and so you end up swelling those. You see they've lost their kind of donut middle part here, and eventually they can break, and that's called hemolysis. And then if it's a hypertonic solution, more water is coming out of the cell than going in, and that leads the red blood cells to collapse, and that's called crenation.
So what does happen to the cells? Like they just disappear?
They die, yeah. So in some cases, this is something that you want to happen. Not the cells to all die, but in some, especially emergency type situations, like shock, you might introduce a hypertonic solution on purpose because you want to increase blood volume as much as possible. So you want to actually draw some of that water out of the cells to increase the blood volume and get more fluids going around the body really fast. But you have to be really careful with that because if it's too hypertonic, you can start killing all these cells. There's also some, we're out of time, but the other thing I like to think of with this, if you take a raisin and put it in water, that's actually an example of a hypotonic solution. There's more stuff in the raisin fluid than in the water, and the water will ultimately go into the raisin and it'll swell up. So everybody's ever tried that before? So you can try that. And then a good example of a hypertonic solution is pickles. If you ever made pickles of any kind of vegetable, you put the vegetable in this brine solution with a bunch of salt and vinegar and spices and everything. And everything moves both ways, which is why all of the salt gets in the vegetable and it tastes delicious. But also, any pickled vegetable is going to shrivel a little bit compared to where it started. It's going to get a little bit smaller, a little bit wrinklier. And that's because more water is coming out into the highly concentrated brine than going into the cells of the vegetable. All right, so we'll stop there. So we'll actually get to play with some of this stuff on Monday. We'll use some dialysis, or Tuesday we'll use some dialysis membranes and see what can pass through them and what can't. Oh yeah, and so if you got C on that one, let me know so I can change your points.